Yeah. Thanks, Pietro. Can you hear me? So yeah, so this is exactly what I want to talk about. So it is maybe more like simple or basic talk than some of the talks that we saw last week, but still I have impression that not everyone really is 100% comfortable with these W-algebra things and so on, which play an important role when we study BPS states, I would say. So I kind of, the first part of the talk, I have some kind of basic overview, and then at the end, I have some simple application to like free field, which sounds maybe even maybe too much trivial, but it shows kind of rich structure of the Bethe equations that one finds in the context of 2D CFT. But before starting the talk, I have two slides about how the Bethe equations for 2D CFT look like. So that's this second line. They are very simple in some sense, and for those of you who know Bethe equations, the original ones written for the Heisenberg XXX spin chain with SU2 symmetry group that were introduced by Bethe in 1931, you see that they are almost identical to those Bethe equations that govern conformal field theory with higher spins, so W-algebras or affine Yangian or whatever way you like to view it. So basic difference, and that's really the main difference, is that this factor, which describes interaction between pairs of particles, instead of being a rational function of degree 1, it is a rational function of degree 3. That's the only kind of jump that you have to do in order to describe the richness of W-algebras, Virasoro algebra, and these things, which have quite rich representation theory. And it took roughly 80 years, maybe a bit less, until people really realized that that's all that is needed to understand the CFT from the point of view of integrability. These equations, I don't really know who wrote them first, but in the paper form, I know them from Litvinov's paper from 2013. But if you look at Nekrasov and Chatashvili's paper, they already have TPA limit of these equations. So probably they already knew the equations, but they are just not written in this form before taking the thermodynamic limit. Okay, so let's write everything. And then there is another set of Bethe equations which also work in CFT, but this time I have to specialize to Virasoro algebra. So there are equations of this type. And again, they are in some sense degree 3 generalization of maybe the simplest possible Bethe equations that you can imagine, which are the saddle point equation for eigenvalues of the Gaussian matrix model. Okay, so I can start with these equations, generalize them by making again the interaction instead of linear to cubic, and that describes free boson, as I will discuss at the end of the talk if I have time. And finally, if we replace this quadratic potential or linear force by arbitrary homogeneous polynomial, then we describe eigenstates of Virasoro integrable structure, the BLZ equations in these guys. Okay, so these are kind of the main subject of what I want to talk about. And in the last part, I want to explain, if I have time, how these equations show up in the local limit of these equations. I mean, probably that depends who you ask, but for me, it's any set of kind of algebraic equations which you solve, and from the solution you can construct eigenvalues of infinitely or large, commuting family of Hamiltonians. So if you have quantum integrable system, you typically, or I think always, have a large family of commuting quantities. You want to diagonalize them, and if you translate the problem into set of algebraic equations, but not arbitrary, because we could also say that characteristic polynomial of the operator is also algebraic equation. But these equations always have this flavor that there is some kind of pairwise interaction between particle-like things, these UJs. Each UJ, okay, I did not really explain the details, but uh, uh, there is always certain number of particle-like excitations. Each of them has associated to it one complex number, uj, It can be the rapidity or whatever of the particle. And then the Bethe equations structurally look like this, that there is pairwise interactions. So you fix one particle, the uj, and then you write interaction term between the jth particle and all other particles that you have. So this is this term or this term. And then there might be term that describes interaction of your fixed jth particle with some external fields. In our case, for Virasoro algebra, it parameterizes the highest weight state. So if you see equations like this, I would call them Bethe equations, especially if you then use them to diagonalize some Hamiltonians. Okay, but the interaction doesn't necessarily be multiplicative. This is some kind of trigonometric aspect of these equations. It can be also additive, like here. But again, you see that there is pairwise interaction between some particle-like excitations, and then there is some interaction with background field, which doesn't which depends only on the jth particle. Okay, so this for me would be kind of prototypical example of Bette's equations. Okay, but the real Bette's equations are kind of these ones with some specializations of the parameters. Okay, so but before getting there, I want to just kind of say, you know, this is the framework what are W-Algebras and so on. So one of the ways, or maybe the simplest ways to describe what W-Algebras are, is that they are some kind of extensions of Virasoro algebra of two-dimensional conformal field theory by higher spin currents. And since basically the only data that gets enters this definition is which higher spin currents you choose, and then you have to satisfy certain associativity conditions and so on. This definition is very general and robust. So because of this, they appear in like many different places. But maybe for purposes of this workshop, it is good to mention that, for example, they are related to superconformal indices of superconformal field theories in 4 dimensions with n equal to 2 extended supersymmetry from the work of Beam, Rastelli, and friends. Or, for example, they can describe the degrees of freedom that are at codimension 2 junction of 3 codimension 1 defects in Kapustin-Witten twist of n equal to 4 super Young-Mills in 4 dimensions. Yeah, or for people who like AGT and Nekrasov instant partition functions, they also kind of appear in that context mathematically. There are different kind of realizations as some kind of action of natural actions on equivalent cohomology of instant normalized spaces. Okay, so but they appear also at many other places. The place where I learned about them is that they describe boundary gravitons in the ADS3 CFT2 duality and so on. So the simplest one, I think these slides I can go faster. The simplest one was constructed by Zamolchikov already 1 year after the famous Belavin-Polyakov-Zamolchikov paper. So that shows how natural the construction is. So he just started with Virasoro algebra. He decided that he wants to extend it by additional spin-free current, which kind of imposes this type of OPE between the stress energy tensor and this new current W. But in order to close the algebra, he needed to find also what is the operator product expansion of W with itself. And he found the answer, kind of unique, of this form. So you see that if you choose this approach, the things get very messy very quickly, because this is like the simplest W algebra after Virasoro algebra and already has many terms. But all these things, they are completely fixed in this case actually by Virasoro subalgebra. But they have meaning. So for example, these factors 5c plus 22, you know, that has meaning because it blows up at the central charge of Li-Yang model, which is a model which has Virasoro symmetry and W3 symmetry. So although this looks complicated, it really is telling us something. Okay, but one thing that is important that you should notice is that the algebra is not linear in terms of the stress energy tensor and W, because there is this field lambda, which is a stress energy tensor square. Okay, so the algebra is intrinsically nonlinear, and that is not a bug, but really something that you should expect. So the reason why Virasoro algebra or affine Lie algebras are linear is just that the dimensions of the spins on the left-hand side of OP are too low to be able to have some nonlinear terms on the right-hand side. So just counting, with fingers on your hand tells you that actually nonlinearity is something that you should expect, but it's just an accident that the basic cases that we learn about are linear. Okay, so nonlinearity is really important and should be there. The main kind of subject or the most interesting algebra or family of algebras that I'm interested in currently are the algebras called Wn. So in that case, you decide to have algebra which is generated by fields of spin 2, 3, 4 up to n. Okay, so these are the exponents of simple algebra, complex simple algebra SLN. So you can think that these Wn algebras are related to SLN in the same way as Virasoro is related to SL2. And there are many constructions how started from SL2. You can get Virasoro algebras. So if you repeat these constructions, just copy paste and start with SLN, then you would get Wn. So that is kind of natural way how they show up. And it's also convenient for many things to work with the whole family at once. So not to work at each individual n, like writing paper about W3, W4, but just try to work at arbitrary n. And for that, and the level of W-algebras, there is this infinitely generated algebra W infinity, which kind of contains in it information about all algebras W. And for higher spin people, the analog of SLN is the algebra which some people call HS lambda, which is the deformation quantization of the symplectic structure on two sphere. Okay, but it's not so important. What is important is that this working with W infinity, it's kind of equivalent to working with all W and for all integers n. And maybe 10 years ago, roughly, Gavardil and Gopakumar, in their work of ADS3 CFT2, they kind of constructed first few orders, the first three orders, I mean, at low spins, this algebra W infinity, by really assuming that we have one generator of every integer spin starting from 2 and solve the associativity conditions. And they found two parametric family. The fact that there are two parameters is not surprising. One parameter is the central charge that we always had from the beginning. I didn't talk about it, but it was always there. And then there is another parameter, rank-like parameter lambda, which is kind of the form of this n. Okay, so in some sense, you can think of W infinity also as being a large n limit or n going to infinity limit, but doing it carefully so that you don't lose this parameter n. Okay, this can be done quite easily. And because you started with family which already had two parameters, the central charge and n, and then you ended up also with something that has these two parameters. So you didn't gain or lose any parameters. So that's all the time, maybe nothing more deep. Yes. Yeah, in principle, yes. But the point of when you solve these associativity conditions is typically, if you have some experience with it, you see that the equations are kind of under, like, not enough determined at lower spins, but they become quite quickly very overdetermined. So you have always many more equations than the number of structure constants that you want to fix. So because of that, you kind of don't expect that there will be new parameters appearing at higher spins. And you already know from beginning that you will have to have at least two parameters because you started with something that had two parameters. No, it had NNC, so you don't lose this. You cannot lose these parameters. So you will, that you have something that has at least two parameters, and somehow the lower spin analysis shows that there are no new parameters appearing. Of course, this is not a proof. So for proof, there is this math paper by Andy Linshaw who really showed that there is exactly this two parametric family solving associative conditions. Okay, so this is what I was saying is more like physics kind of argument. Yeah, but that you have to do because, yeah, you have to assume something, and yeah, You have to assume the spectrum. But of course, you can vary that. You can, for example, change this to SO, then you would have just even spin generators. You know, there are variations. And the oldest papers about W-algebras, they were exactly doing this. So there are papers like W-algebra generated by 2 spins, generated by 3 spin fields, you know, and you can explore this, and it's quite interesting. And I don't think so much is known about the whole landscape of W-algebras. Okay. So this W infinity contains information about Wn, and the way it concretely works is that there is this parameter lambda, and if you choose it to be a positive, in principle, you can take it to be any complex or number or rational number or whatever, but if you choose it to be an integer, then you see that this big algebra develops a very large ideal, and if you quotient by that ideal, you get back Wn. So in that sense, it kind of interpolates between all Wn and algebras. And finally, for many things that I want to talk about, it's convenient to add additional spin 1 field, which doesn't couple to the rest, but it is important for counting states and everything. That is kind of like going from SLN to GLN, and also people who do the AGT, they also know that many times it's convenient to consider these U1 factors. So maybe the most surprising result of Gabriel and Gopakumar when it comes to the algebra itself is the fact that there is a triality symmetry. So for every fixed central charge, there are 3 values of this rank-like parameter lambda, which give you the identical algebra. So, and these numbers are typically very, you know, if one of them is integer, typically the other ones are some rational numbers. So you cannot really easily interpret it as a rank of something, but this symmetry is really there. And for proof, we can look at this picture. So this picture shows space, like curves in parameter space of the algebras, where the vacuum representation develops null states. So when the representation shrinks and the algebra reduces to some smaller subalgebra, and you clearly see that there is this Z3 symmetry, or even combined with complex conjugation, it can look as 6-fold symmetry. Yeah, so the axis, this one is, let's say, lambda 1, and then lambda 2 goes somewhere ahead. Yeah, I should say it. So it's very convenient, instead of parameterizing by central charge and lambda, to parameterize it by these 3 lambdas modulo constraint. And if you do this, this is the parameterization which nicely respects the symmetries, okay? The central charge, for example, is determined like this. And then on this, the axis is such that here I plotted lambda 1, and along like axis like here, I plotted lambda 2. Then here you have lambda 3 in some sense. So it is like, it's this 2-dimensional plot of lambda 1, 2, but I tilted a little bit so that it shows the symmetry, okay? And you see, and these are just a few null states, and you see that they intersect in very interesting ways and so on, and that's just what we know as models in Virasoro or W-algebras. Yeah, typically infinitely many values cross actually, because you know, for example, in Virasoro algebra, the structure of null states is, if you have 2 null states, you actually have infinitely many null states and so on. So because of that, whenever you find like 2 curves crossing, actually infinitely many cross and so on, and you also have, yeah, but I also plotted only finite number of curves and not infinitely many, because it's rational in what, like rational CFTs or rational points in this plot. Yeah, I'm not mathematician to really know because there are many intersection points which are not like minimum models of Wn, but they are kind of minimum models of some more general, like this corner vertex algebras of yeah, but there are also intersection points where none of them is integer, and for those I don't know if they are rational. You know, there are some. If you know this, maybe it will be mentioned on one of the following slides. But there is this Gayoto-Rabchak parameterization of this, which they call like corner vertex algebras, and there. I'm not sure if you have algebra where you impose 2 such conditions, if it is rational from VOA point of view. That is like a math question, but many of them are just the usual W and minimum models, which I think they are rational VOAs. This picture is that if you start with Verma module of the vacuum representation, so from physics point of view, it's just enumerating all the local fields. you look for which values of parameters of the algebra there is a certain singular vector or null state. So when you can consistently make a quotient of the vacuum Verma module to get smaller algebra, and that happens for certain values of parameters of the algebra, and these curves are exactly yeah, you can write it either as Cn lambda or lambda 1, lambda 2. You can choose different parameterization, but it's there. Yeah, maybe there will be more concrete examples where you can see it. What parameterization is? Yeah, so here I chose lambda 1 and lambda 2 to be my kind of independent parameters, and then lambda 1 goes along this axis and lambda 2 goes along this axis. So I just drew like usual Cartesian lambda 1 and lambda 2, and then I tilted the axis just to make the symmetry more manifest, but it's just tilted way of plotting Cartesian coordinates lambda 1 and lambda 2. And another place where you can see that yes, or plus maybe complex conjugation, you can sometimes see it. Another place where you can see this relative symmetry is that you just look at this vacuum Verma module. So for generic values of parameters, you look what are all the fields, you count them, that's very easy, and you find that it's counted by this function. On the other hand, what is very non-easy is that mathematicians in 19th century McMahon found that this same function counts configurations of boxes in the corner of a room. These are called plane partition to confuse people, but it's maybe easier to call them 3D Young diagrams. So you just stack boxes in the corner of the room and you impose the usual Young diagram Young diagram rules, but with respect to all three directions. So this thing is counting the same thing. So you have, at least counting-wise, the correspondence between local fields in W infinity and these configurations of boxes. And triality acts in a very obvious way. It just permutes the axis. Okay, so that's very nicely combinatorially realized. And also other properties of the algebra are very visible in this picture. For example, this truncation to Wn just corresponds to restriction to having just n layers of boxes in one of the coordinate directions. Okay, so it's very natural, and basically all the representation theory of Virasoro W-Algebras somehow translates to very nice combinatorics. You can also consider more general configurations, like configurations where there are some non-trivial Young diagram asymptotics. This should go to infinity along all three axes. This you can use to parameterize different primaries. So yeah, and where do I? Here, yes, because there are, so like in Virasoro algebra, you can choose the highest weight, the conformal dimension, to be any complex number, if you're a mathematician. But this interpretation in terms of asymptotic Young diagram only works for certain quantized values of this conformal dimension. So that's what you would call the generator, maximal degenerate representation. So this is just a subset of representations. In general, you can have arbitrary continuous values of highest weights. Just like for SL2, the degenerate would be when the highest weight is like integer, for example, or something like that. While the general Verma module, you don't have any restriction on the highest weight, so those would not be representable like this. No, yeah. I don't think so, because they work kind of for finite n most of the time, which means that you cut this already. Yeah, so they only have to, like, and then yeah, maybe I will tell you later, because I should think what are the highest weights in there. But they use this. They have definitely these degenerate primaries, because all the boxes in their setup correspond to boundary gravitons. And then yeah, now I remember there is this kind of nice, but I think it would take too much time to explain. But it's nice that one of them is parameterizing the gravitational like bulk solution, and the other one is parameterizing, in context of this Vasiliev theory, the light excitations of scalar on top of that gravitational solution. And this triality in that context is very interesting, because it's telling you that there should be duality where you exchange the gravitational part for the scalar. and you get the same thing, but you have to go through kind of strongly coupling regime to do it continuously. And if you do that, you lose the possibility to describe in terms of Chern-Simons theory and so on. So yeah, so they have this type of things, but with just one asymptotic cut of. Yes, so that is the paper of Gabriel, no, maybe Gopakumar and Joris Raymakers and maybe Eric Perlmutter. I don't know, maybe there is also Alejandra Castro. They have paper where they study that kind of black hole. They call it conical surpluses, that kind of requirement of trivial monodromy around singularity in the bulk imposes this quantization condition here. So you can also generalize this a little bit more by making like periodic partitions, which is describing the minimum models. So something like this, and you had to add boxes, in periodic way. And that describes the minimum model. So for example, this is the vacuum representation of Liang model. This is how the vacuum configuration of Ising model would look like. This is the non-trivial primary delta minus 1/5 of Liang. So you see that it is like, you can obtain it from here by adding this infinite column. So we turn on one asymptotics, we change the primary. And finally, you see that there is some interesting interaction. This box is very interesting one. And yeah, anyway, this is just illustration of some excited state, some descendant. If you work in with this W-algebra description, the operator product expansions get very messy. So this is like example of OP of spin 3, spin 5, and it's just maybe 1/5 of the result. So that's really not the best way to do calculations. But advantage of it is that it's really local CFT description. So you can do many things that you know in CFT. And you can, maybe surprisingly, you can kind of write this in closed form. So you can guess the formula for all spins. But there is a better way to organize the algebra, which is this affine Youngian description. So there is very different, like completely, at first sight, you would not recognize that it's describing the same algebra. There is very different description in terms of Youngian of free boson of GL1 hat, which here I wrote it following Cymbaluk and Arbesfeld-Schiffman in terms of associative algebra with generators and relations. So this is maybe what people who like DIM, the quantum toroidal algebras, would like more. So you have three sets of generators, Cartan-like commuting quantities psi, and then creation and annihilation operators E and F, and they satisfy a lot of relations, but those relations can be kind of written compactly, as you will see. So this is one part of the relations. This page are like quadratic relations between the generators, and then there are also some cubic relations, which are kind of some generalized Serre-like relations. Yeah. So, but the good thing is that you can write the whole algebra on like 2 slides. You don't need to write infinitely many OPEs. And just as in the case of W infinity, it is parameterized by 3 parameters. So this sigma 2 and sigma 3 are parameters, continuous parameters of the algebra, and they can be conveniently expressed as symmetric functions of 3 Nekrasov-like parameters epsilon 2 and epsilon 3, which are related to the lambdas that I had before. Okay, and it's neither a Lie algebra nor a super Lie algebra or anything, because you see that the defining relations have both commutators and anti-commutators, but whether you see commutator or anti-commutator is not related in any way to the grading or filtration. So it's just not a super Lie algebra or Lie algebra, unless you put sigma 3 equal to 0, but that's very special case. Okay. To drop this, I mean, yeah, I was asking myself this question since 10 years ago, but now I would say if you do it, many nice things break down. So it's kind of important for many things. The Nekrasov has papers where he tries to also upgrade this to higher dimension and so on, but those things that he does, I'm not sure if they have some kind of known connection to VOAs, to the, yeah, that I don't know, yeah. But definitely there is a lot of space for generalization. For example, Wei Li with Masahito, they have many papers where they make different generalizations, like not going to higher dimension, but more like horizontally finding like much more extended like structures that have these things inside, and they kind of combine it together to make many much more complicated algebras. But it's not, as far as I know, increasing the dimension. No, you are still in this 3D setup. Yeah, yes. There are many things that break down. You will see maybe on the next slide. Yeah, this is the picture that I generated using ChatGPT. So this, for example, will break down if you go to higher dimension, which I can tell you. These commutation relations that look like most scary, they can be simplified quite a lot if you introduce generating functions for these generators, and then they reduce to some kind of exchange relations between these generating functions. So that kind of tells you that the algebra is not as horrible as it seems. And all is controlled by this one rational function phi, which is just the function which has 3 zeros and 3 poles. And this function encodes nothing else than really the configuration of the elementary box that you have in this box counting picture. So the blue dots are, let's say, the positions of poles, and the red dots are positions of zeros. And then this first zero or pole cancels with this one exactly because of the Calabi-Yau condition. So if you didn't have it, there would be something strange happening here, but many other things would break down. You can do it, but yeah. I feel like, yeah, I feel like too many things kind of become more complicated. It's used at many places, this condition. It's scattering phase that between these particles that I wrote on the first slide. It's this function here. So if you like this as physical particles, you see this is the function phi, evaluated at u1 minus uj minus uk. So that's maybe the thing that I can imagine, that it's interaction between particles or scattering phase between particles. But yeah, probably you can. I mean, this algebra in all the examples that I know has meaning of algebra of adding and removing boxes or excitations or boundary gravitons. For example, so for example, there is one nice system which is just particles on, I guess, circle or maybe real line interacting with delta function potential, where so the Hamiltonian is very like simple, what you would write, again, like 100 years ago. But if you calculate from that system somehow what is the scattering phase, so if you take two particles very far, you send them in opposite directions, they somehow interact, and then again you look at them at opposite asymptotic infinity when they exchange their position, you compare what is the phase function, phase shift of the wave function relative to free case. That's exactly what this thing is measuring in that system. But yeah, the algebra is just algebra of adding and removing excitations, which is exactly what the Youngians do in spin chains and so on. They are really ladder operators but also for instanton calculus and so on. These algebras just add or remove instantons. So they always act as yeah. There are many people here maybe who would know how to answer better. Pietro, you know. There, I think it comes geometrically from this equivalent Euler classes kind of. It's the combination that appears there when you write the algebra. I mean, yeah, I cannot, this type of factors appear when you write this. Yes. Yeah, in that sense, yeah. But if you have like particle-like interpretation, really like this delta function interacting particles, then it's really the scattering phase. And that's exactly, yes, definitely. And also all this paper of Nekrasov and Chatashvili, they write thermodynamic with Ansatz equations, but there the central part that enters this integral equation is the logarithmic derivative of the scattering phase, and that's exactly this one that enters there. So it is really the scattering phase that enters here. And yeah, here it's just, here you see that it's just kind of telling you if you exchange two particles. In some sense, if you add two particles in two different orders, that they differ by this phase. So this also tells you that it has kind of this interpretation of doing something in one way and the other way. I think I will never get anywhere. So in the talk. So then this function is very useful for studying representation theory. So basically anything that you can write with the representation theory can be encoded in this using this phi. So for example, these psi's, which were the commuting quantities, you can diagonalize them in representation spaces, and then their generating functions of eigenvalues are written very nicely combinatorial in terms of this one function phi and the combinatorial like geometric position of the box in this picture. The ladder operators, you see they act by adding box to configuration like this. Again, they can be written in terms of something which I call here E, but E can be again traded for phi and so on. So phi encodes everything. And if you ask what is, so what I didn't prove, and I'm not going to prove it, the first algebra that I described is W infinity, and this affine Yangian, they are really describing the same algebra, but from different point of view, so they are kind of the same object. So if you unwind, kind of the generators, they are labeled by two indices, what I would call spin and the mode, Fourier mode. And so I plot this Fourier mode schematically horizontally, spin vertically. So if you studied operator product expansions, you introduce generating function by summing over all Fourier modes at fixed spin, and then you write OPEs between these horizontal fields. On the other hand, the Yangian description, there you focus on mode number 0, -1, and 1, and you introduce generating function for all spins. And then again, you study some kind of exchange relations between these. So these two descriptions, they kind of focus on different part of the algebra. What is happening in this corner, as far as I know, there is no like really nice, simple, satisfactory answer, but there is the description in terms of shuffle algebra by, I guess, Negud and Symbolic, and maybe also Fagin and friends before. Yeah, but people don't use it so much, and it has also some drawbacks. Good. I mean, in principle, you can calculate it at any finite distance. You can kind of calculate it. They generate the algebra, but if I ask you what is the exchange, if you are very deep, yeah, that's this shuffle algebra description. But you cannot kind of write in any simple way. For example, as far as I know, this J cannot be written in some nice way in terms of his shuffle product, because the Fourier mode of Negut is controlling. So he describes it in terms of algebra of symmetric polynomials of arbitrary number of variables. So not infinite number of variables, but he has symmetric polynomials of one variable, two variables, three variables, four variables, and so on. And all these together, they kind of describe shuffle algebra. So if you wanted to sum in this direction, you would have to sum over varying number of variables somehow, which I just don't know if you can really do it kind of nicely. So this one, the Yangian goes only up, but there is this trigonometric deformation, this quantum toroidal algebra, which has a similar structure in many ways, and that one goes also down, and it has some kind of extended symmetry, like SL2Z symmetry. Uh-huh. What was the last? Yeah, definitely. You have to do some kind of you have to consider some completion. You need to do infinite sums and so on. You have to do something that is not very natural from VOA language, but at the same time, all these things act nicely in representation. So, for example, you have to do. But this is quite common in VOA that you have to have some infinite sums which act kind of locally nilpotent or whatever how you call it, so that they are well defined on the high state representations, but you need to allow for these infinite sums to do the transformation. But to be honest, like to go from this to this, you don't need to do anything more wild than what VOA algebra people would do when they want to write Fourier modes of some composite field. You have to do similar type of sums. So it's very similar. Uh-huh. I mean, Schiffmann-Vassero is underlying a lot of this. For example, the map between these two things. I think it's kind of one way of reading the Schiffmann-Vassero paper is that they describe this map with intermediate step being the degenerate, spherical projection of degenerate double affine Hecke algebra. So they kind of describe this thing, but I don't think they talk about again this like too much about this. In the principle, everything is well defined. From math point of view, it's all fine. But if you want really formula to be able to use for anything, I don't think they have anything useful. I think the most useful thing what Nagud has in these shuffle algebra papers. Yes, yes, but this one has it broken. At least it doesn't look like the symmetry is there. Yeah, this is what mathematicians would do, and they actually prove many things in quantum tutorial. But there are things, as far as I understand, there are things that you can do with these things and not with the quantum tutorial. But maybe I'm wrong. But all the CFT things, like you can study modularity, all the things that from physics point of view you can do with any VOA or conformal field theory. There are some of those that you cannot do clearly in the tutorial setting. And also, I don't understand what is like the really physical meaning now, not from point of view some higher dimensional supersymmetric theory, but really of 2 or 3 dimensional physical system where this toroidal or the Q-deformed algebras. I don't know, for example, system where which I would consider physical and the Q-Virasoro would act naturally, because those things are kind of non-local, and I don't understand the character of that non-locality. But you are right. Like if you are a mathematician, definitely a lot of people, even some people in this room, they would tell you that it's much easier to do things in the quantum toroidal algebra because of these additional symmetries, and then take the limit. Yeah, that. Time I should finish from now. Okay. Mm. So this is what the algebra is. Now I wanted to talk about these integral structures. So picking some kind of commuting Hamiltonians in the algebra and diagonalizing them. So that's a simple question. So there are different choices. So unlike in SLN, there are different choices of which Hamiltonians you can choose. So for example, and they are distinct. So for example, in this description of the algebra, it's very natural to take these psi's to be your Hamiltonians because they commute and they are infinitely many. So you have very good chance of describing many things by studying their eigenvalues and spectrum. And actually, if you do it like this, then the eigenvalues are very easy to write down. That's what was on one of the previous slides. Everything is determined in terms of combinatorics of plane partitions and so on. And there are people who study it like this. On the other hand, if you want to stick to this physical CFT point of view with local operators and so on, the problem of these Youngian charges is that they are not local. Whatever, I mean, if you know what it is, then you know what it is. If you don't know, I don't think I can explain quickly. Maybe you'll see on one of the slides example of this non-locality. So there is another set of quantities which were studied in context of Virasoro algebra by Bazhanov, Lukyanov, and Zamolchikov. They call it quantum KDV system, which are nice from the CFT point of view, but their spectrum is much more complicated to describe, like explicitly. And what I have on next few slides, but I think I have to skip it or do it very fast, is that there is a way how to connect these two by constructing a continuous family of commuting Hamiltonians which interpolates between these two. And this, I guess, I know it from Litvinov's paper, but in the quantum toroidal context, again, there are people like Feigin, Jimbo, Miwa, Muchin who study this problem. So that's along the lines that you say. They study it in the toroidal setting where they can do many more things, and then they take the limit. So before that, I had one slide. Maybe it's worth going through it of like physical interpretation of what these commuting quantities are. So in the classical limit, the Virasoro algebra reduces to the algebra behind Korteweg the Friese equation, or the Karamsen-Petviashvili hierarchy of integrable PDEs in the setting of W infinity. So if we stick just to the Virasoro case, the classical object that is related to stress energy tensor of Virasoro algebra is this Schrödinger potential U, and geometrically it's more convenient to consider the Schrödinger operator d square over d over dx square plus the potential. So it is well known, at least from maybe 70s, that there is infinitely many continuous deformations of this one-dimensional Schrödinger potential, which preserve the spectrum of this operator. And they are organized into commuting flows. So the first such flow everyone can write down. So if I just rigidly translate my Schrödinger potential, I don't change the spectrum. But there are infinitely many more, and they are nonlinear. They really deform the potential, but they preserve the spectrum. So the simplest one is this KdV equation, which was written in 19th century. And you can interpret it in terms of Hamiltonian system. So you have Hamiltonian system of like infinite dimensional one of all Schrödinger potentials. You can introduce their classical Poisson bracket, which maybe looks complicated, but if you Fourier transform the right-hand side, so if you consider this variable to be on circle, then the Fourier transformation of this is just classical Virasoro algebra. And then these flows in the space of potentials that I mentioned on the previous slide, they can be generated by Hamiltonians. The first Hamiltonian is just the zero Fourier mode of the potential itself. The next Hamiltonian is the zero mode of the square of the potential, and so on. So these all commute under this Poisson bracket. They deform the potential, and by construction, they are also conserved during the flow because they are the Hamiltonians. So they give you infinitely many conserved quantities for all these deformations. This integrable structure of the Virasoro algebra is exactly the same, but in the quantized setting. So again, you can write these first two Hamiltonians. Now you have to, when you want to write square of the stress energy tensor, you have to a little bit be careful how to define it, but that's kind of standard thing. And in principle, you can write infinitely many such objects which commute, and you can ask yourself, what is their spectrum in the representation spaces of the Virasoro algebra? So it looks simple because one of the generators is the Virasoro L0. So typically you really have to diagonalize finite matrices. So it sounds from math point of view as a trivial problem, but of course you want to have some explicit description of this, not just say that you can diagonalize it. So for example, at level 5, you can calculate these matrices, and they are just some random rational functions of the central charge and the conformal dimension of the primary, and you just can put it in Mathematica, find the spectrum, but you learn nothing. No, so the question is how to describe the spectrum in some geometric way. And the surprising answer was found by people who worked on OD IM correspondence, so like Dori and Tateo understood how to do it for the primary state, and then Bazhanov, Lukyanov, and Zamolchikov understood how to do it for all the descendants, so for all these Young diagrams. So what they say is that you should study this very simple quantization of the Catalan curve. So you take a curve which is like y square plus z to the n. You kind of quantize it, promote it to differential operator, and that is supposed to describe the primary state. If you then want to describe descendants, you add some apparent singularities. So you add some additional singularities in the complex Z space, and you require then that these new singular points, they are apparent. So you can say, let's say that the Frobenius solutions around those points are just power series solutions. There are no logarithmic terms, no monodromy around those equations. To calculate this, it's quite easy. It takes like, you know, 1 page, and you find that this is only satisfied if these positions of these added singular points satisfy system of Bethe equations that look kind of like this. Okay, so this is really the exact equation with no simplification, which describes any descendant in any, let's say, Virasoro representation. Okay, and you see that there is some interaction of the kth particle. Sorry, this x should be z. I just changed the notation. It's the same thing. X and z is the same. So it describes the interaction of this zth particle with some external field, which in this case is just the nth order polynomial, you know. And this describes the primary field. For example, if you have delta equal to 1/5, like on previous slide, finally this describes the interaction between particles. So this is, I should say, this is not the original form of BLZ equations, but this is like simplified form that was, I know it from Fioravanti's paper. Okay, so if you write it really the way BLZ wrote it, the equations are much more complicated. They call it monster potentials, but in the end, if you do some simple transformation, change of coordinates, you get this nice form. And then once you solve those algebraic equations, you can extract all these higher Hamiltonians by just plugging these solutions, the Bethe roots, into some polynomials. Okay, so here I wrote it really exactly. So I didn't do any simplification, but basically what you see that there is some contribution of the highest weight state to this first non-trivial quantity I3, and then there is this very simple polynomial in Bethe roots, which describes the whole spectrum of this I3 for any descendant. And M is the number of these apparent singularities, roughly. Ignore this n+2, I don't want to. That's exactly the Fioravanti's improvement that he actually describes it as orbifold of this with respect to symmetry Zn+2. But I don't want to talk about it because I just don't have time. But it's roughly, you can think of them as being m of them. Then it's describing the number of boxes, number of particles, you know, the L0 eigenvalue, all these quantities, number of instantons, you know, all these quantities, they are the m, the number of them. No, m is the level, Virasoro level, and n controls the central charge, and L controls the primary, so delta. That I didn't talk about it. Now I'm talking about the local side. So, and next I should say this deformation. This is the undeformed case, but not the Youngian one, but the local. So this is the other extreme limit. So, yeah, here I have few slides, but I have to skip how you construct these Hamiltonians. So basically you can apply the whole, the standard procedure of algebraic Bethe Ansatz. So you can start with what some people call instanton R matrix, which in this setting is really a thing that somehow links this affine Youngian. I mean, there is the central object, which is this Miura transformation, which we also saw last Monday. And this, you can interpret it as free field representation of the W-Algebras, but also it is something that allows you to define the R matrix and construct the affine Youngian. So it's kind of bridge between the two worlds. And if you have this object, you can just apply standard algebraic Bethe Ansatz to, yes, so I just say, this is how the Miura transformation looks like. That's one way of defining the whole algebra. And it shows that these algebras are really just quantization of nth order differential operators. The instanton R matrix just is the conjugation or intertwiner between two different free field representations of the Virasoro algebra. It satisfies Young-Baxter equation. So if you like algebraic Bethe Ansatz, you can construct the spin chain from this R matrix, and this spin chain produces Wn algebra, where n is the length of the chain. Okay, so this is a very standard procedure if you know it. And then you can extract the Hamiltonians by introducing some auxiliary space and taking trace of this auxiliary space. In our case, the auxiliary space is infinite dimensional, so you have to regularize it. And that's exactly the place where this deformation parameter shows up. I can take it even more complicated, but the simplest one that I know is the Fock space of single free boson. And then Q, kind of this deformation parameter, which is very important. It controls, let's say, the complex structure of this auxiliary torus when you take trace of it. Okay. So if you know algebraic Bethe Ansatz, the previous 3 slides would be very clear. If you don't know it, then I don't have time to explain it now, but you can ask. And then you can extract out of it these Hamiltonians. The simplest one looks kind of like this. So it is written as a 0 mode of some local field. So this is like a good thing from the CFT point of view. But then there is this Q deformed kind of square of spin 1 current M. So if you completely ignore this factor here, then it would be just the Sugawara stress energy tensor constructed out of free boson. But this kind of non-locally deforms it. So that's the role of Q from this integrable structure point of view. It's really introducing some kind of non-locality of the conserved quantities. Now, if you send Q to 0, which is the Youngian limit, then this non-local factor reduces to the absolute value of the mode, which is the Youngian limit or the Benjamin-Omno limit, and this gives you the quantities which are easy to diagonalize. On the yeah, so I take a trace like this over the auxiliary space. That gives me generating function of the Hamiltonians, and then I do large spectral parameter expansion, and the quantities that I find are exactly these Hamiltonians. Sorry? So they commute with each other at fixed Q and all spins, but if I change Q, the Hamiltonians for different Q don't commute. At fixed Q, they commute. Q is arbitrary, but I fix it, and that kind of tells me which Cartan algebra I have. So I think soon, yeah, anyway, and in principle, you could now continue the algebraic Bethe Ansatz to write these equations, but this is, as far as I know, no one really succeeded to do it in physically clean way. So again, there is this math paper by Feigin, Miwamuchin, and Jimbo, who in very different way kind of calculated this, but it's not really so physically obvious what really, it's kind of a paper which is for me quite complicated, but they prove that this system of equation diagonalizes the Hamiltonians in the Q-deformed setting, not this Q, but in the toroidal setting, and then by taking the Youngian limit, you can write equations like this. And now maybe I just show you a few pictures because I cannot, I don't have more time. So the important point is that these equations, really, although they look very simple, they have very rich structure of solutions. So whatever you learned, if you open differentials or some CFT book about minimum models, null states, and all that, that is all encoded in this simple system. So I have here a picture. So this is like you fix the parameters in certain way. You fix the algebra, the epsilon parameters or lambda parameters to one specific minimum model. I chose the Liang model because it's simplest, it has fewest states and so on. And I just want to show you how the equations, the Bethe equations, how the solutions look like. Okay, maybe I should show it here. These equations are very easy to solve at Q equal to 0 or infinity, okay? You can just put all the denominators to the left-hand side. It's just product of linear factors. When you send Q to 0, you kill the right-hand side. So basically, you need to solve a product of linear equations. That's very easy, but it branches in many ways. And this way how it branches is exactly encoded in this 3D Young diagram. So here you see that these denominators are really telling you that the two neighboring beta roots have to be shifted by either epsilon 1 or epsilon 2 or epsilon 3, which is just telling you in which direction the boxes can sit next to each other and so on. So this is very easy to solve at Q equal to 0. At other values of Q, it's hard, but you can numerically solve it by solving it at Q equal to 0 and deforming it. So for example, I can on this left-hand side, I can just start at Q equal to 0 and choose some curve along which I change Q and then look what the solutions of Bethe equations do. And you see that the roots So I'm at level 2, so every eigenstate is given by pair of roots, so m is equal to 2. They somehow evolve in the complex plane, and they can do different things. They, for example, can have non-trivial monodromy, so I can start with one solution at q equal to 0, go along some non-trivial curve and come back to q equal to 0, but the solutions can exchange. So for example, the green solution and blue solutions, you see that they exchange each other. Actually, if you experiment with it numerically, you see that it seems that at every fixed Virasoro level, all the states are connected by this continuation parameter, which is somehow similar to what is happening with these excited states in thermodynamic Bethe Ansatz. Or, and that's the last thing that I want to talk about, but probably I can only show a picture. You can study what happens as q goes to 1. So in this local limit, and you see that the solutions run to infinity, but not all of them. Okay, so some of the solutions stay finite. Here the blue ones stay finite, while the other colors, they seem to run to infinity, and they arrange at this kind of rectangular pattern. Okay, and if you look at it more carefully, and if you look what is happening at the level of the algebra, you see that what is happening is factorization in this GL1 factor and the W infinity piece. So somehow this free boson, which at the beginning of the talk I coupled to the system to simplify the combinatorics and everything, this one seems to be decoupling from the Virasoro algebra and the rest. And the way it decouples is that some of the beta roots that are associated to the W infinity part, they stay finite, while the other ones, they blow up to infinity, and they somehow encode the Young diagram that encodes the excited state of this free boson. So if I just, there is some certain center of mass motion, but if I undo it, you see that the way these beta roots kind of approach Q going to 1 is that there is this kind of pattern of horizontal and vertical Young diagram in some sense. If you look, this is not so visible at level 2, but at level 3, this is how the equations look like. So it looks as complete mess. But again, if I undo this center of mass motion, you see that they are somehow starting to arrange into more regular patterns, and you should be in principle able to read off what is the Young diagram that is encoding the singular behavior of the solution as Q goes to 1. And that was what I wanted to discuss in the last part of the talk, but I don't have time to do it, so I can just go very quickly. So because it has many connections, and that was kind of illustration how these equations, how rich they are. So this limit is very singular, but you can see from the numerics that there are some things that are happening. Ah, yes, let me do like this. So I transported here the solution from origin when I have good control. I transport it to here, and then I can look, for example, what is the monodromy of solutions as I go around the singular point. Okay, so if I do it like that, I move around the circle at q equal to 1. You see that the solutions somehow run into different circles, but you see that the monodromies that are around there are either kind of double monodromy, so the beta root goes from its value to the negative value, and then the other one goes back, so they just exchange their position. Or you can have more complicated things happening. You have some triple monodromy where 3 roots are permuted and so on. But from the experimental evidence numerically, it seems that nothing else is happening. So this kind of motivates the ansatz that you can write for trying to solve the solutions, the Bethe equations in the Q going to 1 limit. So you have these kind of unknown coefficients. And if you plug it into equations, you find that the Young diagram kind of gets translated. I mean, if I give you Young diagram, there is something called 2 core of the Young diagram, which is subdiagram which is obtained by removing the domino tiles of size 2. So if you remove this domino, then this domino, then this, and this, then at every step you preserve the Young diagram picture, but you end up with something that cannot be further reduced. Okay, so this mathematicians call this 2 core. It's some kind of irreducible part of the Young diagram. So the claim is that this part is counting the roots that have triple monodromy, while the remaining dominoes correspond to roots that are exchanged in pairs. You can write equations for these white ones. They are of the form that I discussed before, but just for x square potential, while those you can explicitly solve in terms of Wronskian Hermite polynomials, so you have very good understanding of that. While the other ones, the triple roots, they are much more complicated, but they are related to something that is famously known from math as this, I don't know how to pronounce, AMM locus. Okay, if anyone is interested in it, this is, for example, how this AMM locus looks like at level 15. Okay, and there is very interesting structure related to this KP hierarchy, which controls how these are behaving. But if you want to know more about that, you have to ask me, because I'm already behind time. And finally, let me just say that these solutions can be mapped to what is called rational deformation of the harmonic oscillator. So you can start with quantum one-dimensional harmonic oscillator, and by some kind of known transformation from 19th century, you can pick finite collection of levels and just remove them. That is labeled by Young diagram, and this removal is done by just adding some easily some well-defined potential correction that you can easily write down. And this type of exactly solvable systems, which are the harmonic oscillator minus some states, is exactly the bridge which allows you to show that the solutions of these whatever Bethe equations can be written in terms of these Wronskian Hermite polynomials and so on. I'm sorry I don't have time to explain this in more detail, but feel free to ask me. And sorry for going over time. So you are now asking, look at the algebraic Bethe Ansatz construction of these things. So you can choose the quantum space, which is the one that you are interested in, where the Hamiltonians will act. You can choose with whatever you are interested in. And then for any of these three orientations, you know, Y element, you can choose it as you want. Also the auxiliary space, but the experience is that if you choose different auxiliary space, you just get some transformation between the generating function of Hamiltonians, but the Hamiltonians themselves are the same. They are just kind of trivially, you know, you just have some kind of redefinition of linear combination of these Hamiltonians. So it makes sense to choose the auxiliary space as simple as you want. On the other, so I choose just one boson. On the other hand, if you for the quantum space, of course, you need to choose the one that you are interested in. Uh-huh. Okay. Yeah, that would be very exciting, but I would be very happy if someone finds out how to associate with some vertex of algebra, because that's what I like. Maybe there doesn't exist one, or maybe it's, yeah. So, but I would, this higher dimensional question is something that is very interesting. And for example, I have one paper with Lawrence Everhard that everyone ignores, but I think we found something interesting, which is that at the level of VOA, you can find generalization of W infinity, where you start from like Grassmannian instead of starting from projective space. And then the resulting algebra, instead of having 3 parameters modulo 1 constraint, it has like 5 parameters modulo 1 constraint. But we did not succeed. Sorry? It is too much, but it's not something that we wanted. We wanted one more parameter, but what we found was one more parameter, but in such a way that if you study anything representation theoretic, you find that these 3 parameters want a fourth one, which is equal to 1. And then, you know, so somehow we were not able to really construct this algebra where the 1 would not be 1. But all the representation theory, like, for example, let me just say, at the beginning, I had this, uh, this lot of curves, no? So you can, for example, study this in this Grassmannian algebra, and you find that the curves that are there are not described uniformly. There is not one type of curves that you can write, but there are like 3 types of curves that look different, but they are one if you introduce one parameter equal to 1. And all these things, also central charge, everything can kind of be written uniformly, like in one equation, if you think of having 4th parameter independent, which is equal to 1. And then actually there is also ortho symplectic version of that. And there it seems that everything is again agreeing with the previous one if this parameter is 2. So it seems that there is something, you know, and then it has like 5 tuple symmetry and so on. Yes. Yes. So no, the point is that you can study complicated algebras, but in the end, if you kind of correctly, you know, play with it, in the end, everything reduces to very simple equations. So I want to promote these Bethe equations. But many people have no idea about this, or they don't use it in any way. So maybe you can say that the new aspect is the way. So that's kind of my small contribution that I didn't write down it. How do these equations behave in this singular limit? How to extract the local quantities, and how? Oh, it did happen not in the slides, but in. Okay, it's like kind of this because I didn't write down the paper yet, although we have the results from last year, but there is still something small missing about understanding this part better. So this last part, like how, starting from here, what is the singular behavior of the equations? So this type of structure, like what happens as q goes to 1? No, I have a very concrete understanding. So I understand which beta roots blow up, which are finite, how they blow up, and what are these singular expansion coefficients in terms of these other like classical integrable structures like the this KP, this Adler-Moser. I mean, I understand very well this, and I have a conjecture for this which works for a very high order, and I understand to what structures it's related. So the singular behavior of the equations. Yeah, and the reason why the paper is not written down is that actually finding these y's is something that seems to be very complicated, like more rigorously. So I have a guess, but I'm not even 100% sure that the guess is true because I can only test it, let's say, for first 6 cases. And that doesn't matter. And but then the previous things, you know, these equations and so on, it's not completely historical because there are not really, I would say, enough people who really did some study of these equations seriously. You know, so the way how you extract the Hamiltonians from it, that's part of that I skipped, but that's also kind of half news. Yeah, whatever. I can tell you afterwards. So I don't think it's like completely historical talk, but the main point was to promote the fact that a lot of rich structure is encoded in these simple equations and that they have really very rich behavior.